Hello and welcome back. In this video, we want to discuss almost everything about hypothesis testing. So to begin, let's list down our agenda for today, and that is hypothesis testing, all right? And one of the main components will be claim. What's a claim? How to form a hypothesis? What is a correct or valid hypothesis statement? And next, we would want to talk about distribution. Should we use Z or T? Again, that's perennial confusion, right, in the students. Which one should I use? We're going to clarify that. Then we want to talk about test statistic. Again, a very important component. The idea of test statistic, critical values, value or values, then p-value, and significance level. Alpha. Okay, and of course, not forgetting conclusion, statistical conclusion or hypothesis conclusion. How to make a conclusion. And let's get started. The goal, remember, is that we want to find mu, the population mean, yeah? And let's just put a bracket here, the population mean of X, the random variable X. X can be anything. The height of people in the 200,000 people town, their income, their wallet dollar amounts, their weights, yeah, their heart rates, anything at all, right? Okay, so then through sampling, we have two ways in statistics to determine mu. One is through confidence interval, which we have discussed right at length about in another video. So we're going to put this aside. And the other one is hypothesis testing, which is what we are going to talk about. So if I write HT or hypo test, it just allows me to write shorter. And we want to explore, right? So how do we go about this? It all starts with a situation. It's usually a tense one, not a calm or peaceful or enjoyable situation. Usually a tense one. Why? Because there is, for example, a dispute, an argument, a declaration or proclamation that annoys people, right? For example, I'm the best in doing mathematics. That annoys people, right? That proclamation annoys the competitive students, and so they say, "Are you sure or not?" Right? So there's a dispute, there's an argument. It could be also some sort of a dispute, disagreements. For example, hey, you know, this mobile service company's monthly bills is expensive. They're overcharging, right? Oh, that's a accusation, yeah. So it's often starting with these kind of confrontational situations, sometimes very tense and legal, and that's why it's very important to know statistics, because even in courts of law, the judgment is based on probabilistic likelihood, right? Which party is, based on the evidence, most likely to be uh, correct, and so the judgment will be made in that sense. And then, truth be told, no one knows the truth, right? So it's all probabilistic. And how does hypothesis testing come in, right? So in those situations, there will be an assertion, a claim, right? So what's a claim? A claim involves a statement, all right, a statement about mu. I'm not saying the claim is correct. I'm just saying that the claim is saying this, all right? A claim is a statement about mu, all right? So the claim in real life often exhibits itself as I claim that, someone claims that, right? Someone asserts, someone believes. That's a milder word for claiming, but nevertheless, it's a statement without proof, right? Just usually without proof yet, or not yet, right? So a statement about mu, and it usually goes with these words: believes. What else? Things, right? You can start to get a feel that these are just uh, statements that people say, or just says, right? Opines. I have the opinion that, right? I have an opinion. It's a subjective thing, and these are just words in that are used in sort of layman situation, colloquially, right? So people just say it, but when they say it, you should be on the alert. When you hear these words, they are claiming something. They are making a claim, and usually their claim, of course, is not about mu, but about an adjective. This mobile company's bill is getting very expensive. But hey, wait, didn't you know that it's expensive when you sign up? No, 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 it's getting way more than what I thought I was supposed to be paying. Okay, good. Something fishy is going on. Will the mobile company accept this without proof? Of course not, right? So they're going to not believe in this. So now there's a confrontation. There's a disagreement, right? So usually that's how the hypothesis testing comes into play. Why is there a claim, right? So a claim is a statement about mu. If we say this mobile service company's monthly bills uh, tends to be expensive, or is starting to give us a sense that they are overcharging, right? So that's a very strong statement. Of course, the company is going to disagree, and this statement about mu needs to be translated into something quantifiable. So this statement about mu has to be something quantifiable. Quantifiable, right? So that we can put them into hypothesis. So what's a hypothesis? Let's just have an example. So a claim statement can be, so a claim example. So the mu is very expensive, more than $170 per month on average. So we are asserting that this mobile service company is, on average, charging their subscribers $170 or more. Some may be paying less, but in general, on average, the average is very high, 170 or more. So that's very high, right? Maybe some people will be paying only $50, but some people are paying 270. Some people are paying 320. So that on average, it's probably 185, 182. I don't know about mu, but I'm going to say it's high. High in what sense? High is greater than 170. Right? So this greater than can also be in the same opinion or same expression. This mobile service company's average monthly bill is high, right? High in what sense? Greater than 170, or greater than or equal to 170, right? Or not less than 170. So I claim that their average monthly bill is not less than 170. So that's greater than or equal to 170. So no matter what I claim, the claim is the same, that they are expensive, right? I'm just putting down two additional things. One is the greater than operator, and the other one, or the greater than equal to operator, uh, or and the additional information, 170. So it's not 17, it's not 1, it's 170. So that is a claim. A claim is this statement that mu is greater or greater equal to 170. Right. Another example, this particular cancer analysis, right, of the blood sample or bone marrow sample or whatever, has cancer. This sample has cancer, right? Now, this is a very serious statement, right? So there's no confrontation, there is no argument, but at this point in time, maybe the doctor, maybe the lab analyst has to sign over it with their given authority, right? So when you sign over it, you're going to announce this bad news to the patient, and you better not make a mistake because it's very serious, right? There is not yet lawsuit, but then if you make a mistake, then of course people are going to be unhappy or make the wrong decision. They think they have cancer, they donate away their life savings, only to realize it's a mistake. So but you have donated, and so what happens, right? So it can be very, very serious. So now the doctor is going to claim, right? The doctor is going to claim that the blood sample has cancer. He's challenging himself. So he's going to say, I want to say that this blood sample has cancer based on what I see. Is that right? So based on my diagnostic of the patient, right? So I'm going to take the blood samples and analyze them. So the population mean of all the blood samples of this patient. That's we have to define this mu very carefully. Yeah. Has cancer means in some medical measurements, you can measure the cancer cell, that means exceeding certain number. But we have this greater than example. So we're going to not too artificially pick another measure, another medical measure that says if your amount of red blood cells, right, is going to be on average below some number, say 100, millimole per gram or whatever, is the suitable unit. So the unit is very important because when unit changes, the number here also changes, isn't it? By 1,000, by other multiples. So you need to put down the unit. But we're not going to concern too much with ourselves with the medical justification. Just that the claim is that if this happens, if this happens, then mobile service company is expensive. If this happens, then the patient has cancer. All right, because the blood cell amount is too little and has been affected by the cancer. So that's why it's very serious, right? Next, we are going to say something like, some student claims that, right, say this university's students' average GPA. So mu is the population mean grade point average of this university's students is 4.3 out of 5, let's say. Okay, so this may be a student's guess. This may be the admissions office guess, because admission office might not see past students, very, very early students' GPA scores already archived. This could be a student debating, arguing with another student, right? So whatever it is, let's say that there's this statement, right? So the student claims that, hey, you know what? our university's average GPA is 4.3, so not too bad. Right? Or maybe the student is trying to debate with the parents. Parents say, hey, this university is not so good. Student says, no, this university is, average GPA, graduating students, 4.3. So yeah, let me go in there. My friends are all there, right? So you can imagine many, many situations that give rise to some assertions. Typically, our assertions will be adjective-based. This university is very good, right now, yeah? But very good from the student's mouth, very good means what? Means a lot of students there. That's not convincing to the parents, right? Means GPA is very high, right? So yeah, that could also be a case of greater than 4. Possible, yeah, but we already have a case here, right? So we're going to just give this particular example that the student specifically says this university's GPA, I know, I asked a few friends already. The average should be 4.3, maybe 4.2999, but let me just say it's 4.3. Right? So let's just assume that's the story. And next, we're going to put down the hypothesis, right? So form hypothesis. The way hypothesis statements are being written in statistics is going to be a very rigid one, rigid in a good way, because if it's rigid, it means you don't have to exercise a lot of creativity, which means it's almost like form filling, which means it's good because it's a standardized way of laying out the steps and numbers so that everyone can understand. It's like Mozart wrote down the music not in a way that he likes, right? Not in a sort of a carved wood that he likes, not in a way of a folded paper that he likes to write music in, but he uses the internationally recognized music score notation. So when he does that, everyone, right, whether you're a violin player, you're a piano player, you're a cello player, you can read the score and you can play out that beautiful composition. So same thing here as in statistics, there is a so-called music score notation, but these are in the alphas and betas, but they are no more difficult or not much easier than the musical notation. So I totally appreciate that. If you find this a little bit challenging, I understand, because if I look at music score and the tadpoles that jump around the lines, I hardly can understand what they are doing without serious study and practice and training. But if you're very into music and you can read music scores like nobody's business, and you can play piano like nobody's business, you will say it's so easy, right? But I will look at you with a lot of envy, and you will tell me, just practice hard, right? You have to put in the time and effort. And that's what I'm telling you now, right? So put in the time and effort. It's not that hard, but we'll do it slowly, right? With my guidance. Okay, let's move on. So to form a hypothesis, we need a rule. And here's when students do a lot of mistakes, because sometimes they guess. I hope that's not going to be you, right? Sometimes by chance they are right, but there's a 50% chance that you are wrong. So I'm going to give you a rule. The rule is that all the claim statements, all claims go into H1, hypothesis, alternative hypothesis, right? Except, there's only one exception. So except for equality test. Equality test is when the statement involves the equal sign like this. Solely equal sign. So this less than equal doesn't count as equality. So this is the equality. Equality statement, right? Let me just quickly quote an example here. Mu equals to 4.3. So only this case counts as equality statement, the pure equal sign. Okay, so having an equal sign in the greater than or less than, they don't count. They are not equality statement. They are like the inequality statement. Okay, so now that we have clarified that, and you understand that there is this golden rule, this not golden rule, secret rule, right? To put down the claimed statements properly, now it is a lot easier. How come? Because we're going to see that claim statement always go to H1 and not H0, except for equality statement, which goes to H0. Okay, so let's try it out. In the first case, someone claims that the mobile phone company is charging expensive monthly bill. Expensive translates to the population mean monthly bill or is greater than or greater than equal to $170 per month. Right. So this is a claim statement. All claim statements go to H1, and this is not equality. So we are going to write H0, H1. H1 is going to be the claimed statement as is. Okay. And of course, if it had been greater than equal to, for example, the person says the population mean monthly bill is no less than $170 per month. No less than translates into greater than equal to. So why don't we write greater than equal to? Because the statistics convention is to push the equal sign, all the equal signs, to H naught. Understand? Yeah, push the equal sign to H naught. So we will end up having the opposite and the equal sign like this. This is where students in polytechnic, A level, or even high school, when they are taught statistics like this by their teachers, maybe it wasn't explained completely. Maybe the teacher himself or herself was taught wrongly, and so end up every time students saw the claim having an equal sign, literally, right? Literally, there's an equal sign. There's equal sign. So it becomes the claim statement becomes H naught. That's wrong. Oh, that's wrong. I mean, look, these two, in actual fact, when it's expensive, whether it is greater than 170 strictly, like 170 and 1 cent, or greater than equal to 170, like 170 and 1 cent and 2 cents and 3 cents, doesn't make much of a difference, right? Why would the positioning of that statement suddenly jump from H1 to H0, so long as 170 itself is included? That's absurd if you think about it. That's too drastic, right? Yeah, so the idea is when the claim is having inequality, right, that claim statement goes to H1. That's the opposite of saying this. When there's inequality, whenever there's inequality, it goes to H1. When it's exactly, strictly equality, then that statement goes to H2. Okay, let's try the second one. The second case, the dispute is there is cancer, right? There is cancer if the blood cells count has less than 100 some units, some medical units, or less than or equal to 100. Right? So this is a claim statement that is not equality, so it goes to H1. So we write mu less than 100. Even if the original statement was less than or equal to 100, we write less than 100. But we will then shift the equal sign upstairs to H0. All right. And the third case, that the population mean GPA is 4.3, right? So is this good? Let's say. So we'll write, because it is the equality statement, we'll write the claim statement in H0. Like this. You can also reason it as the original statement also goes into H1. But because there's a statistical rule that moves the equal sign to H0, so we first put mu equals to 4.3 in H1 as per the rule, and then we apply the statistical rule and move it to H0. right? If you like to understand it that way, that's okay. But of course, finally, you still write mu equals to 4.3 here. Yeah, okay, so that's going to hopefully eradicate all the incorrect thinking, all the guessing work, and you start off clean and correct at this point. Okay, so very important. So now that we have done the claim, what is a claim, right? How do we quantify it? And we always will hear claims and assertions and declarations that are not quantifiable, okay, that hasn't been quantified yet. When you say, for example, you hear a student self-proclaiming, "I'm very good in math," right? Well, you're not happy with that kind of arrogance. Then you say, "Okay, good in math. Good in what sense? Can you do 10 questions in 3 seconds?" You start to have some numbers to perform measurements, right? The ability to measure the abilities. Or you ask, how many questions can you do? How many math puzzles can you solve in 10 seconds? Then it is a open-ended quantity, and so you can say, if you're good, then the average should be at least 8. Yes, right? Because the first trial, the first 10 seconds, the person has just started to warm up, solved 5 out of 10, like as if it's that bad. Of course, he's not happy. He's going to say, let's try again, right? Out of 5 sets, I should be able to score at least 3 sets that are 8 or more, right? Something like that, right? So you will say that the average of all the 5 sets should be at least 3.5 and above out of 5. So a claim will be that statement. I'm very good, right? Or GPA is 4.3. Or population mean measurement has that amount or less, or that amount or more, that kind of thing. Now, it is important to understand that the hypothesis statement is always about population mean, the number that we want to know, but cannot find out. Sometimes can never find out. For example, astronomical scientists will want to talk about the average brightness in that sector of the sky. Average brightness. Do you know how many stars there are in a particular sector of the sky? Well, latest knowledge is billions and billions of it, like totally countless. Countless is the right word, countless. You just cannot afford the time to count and finish counting them all, just in one corner of the universe. And how to find the average brightness? Well, first of all, the answer is there, right? It's not infinitely bright. It's not complete darkness. There's some amount of light. Yeah, so there is an answer. There has to be a finite answer. But then until you find out the brightness of all stars, you cannot answer that question in a strictly correct manner. So again, you see that we want to find mu so that we can have a good textbook about our understanding of the universe or whatever it is for scientific purposes, but we can never find it out. So one way is to perform a hypothesis test. Of course, we can do confidence interval, which is probably a better way to range bound the brightness, the average brightness. Yeah. So it's about the population of all stars by sampling a few stars that we can observe, and over several random nights in the whole year, we hope to be able to obtain sufficient sample size, right, to estimate correctly the average brightness of all stars. Clearly an effort that is impossible to achieve, right? All stars. But through sample exercises, we are able to measure finite number of stars, their brightness, and then estimate. So we can claim that, yeah, the average brightness is at least that much. If it is at least that bright, then scientists can make further interesting guesses about the behavior of the universe, right? If it's that bright, that means there's a certain amount of energy. That means there should be a certain amount of mass. That means this and that, and so on and so forth, right? So they can have a better anchoring of their further guesses. But if this is not true, then we have a problem, right? So now what happens? Well, what happens is, what is our attitude when we perform hypothesis? what is our disposition? How do we treat our hypothesis? So here's the kind of posture that we take, right? So when performing hypothesis testing, right, we always assume H naught to be true until, that is, we take mu to be same value as our hypothesized mean, mu naught throughout calculations. Until data shows otherwise. And that's our conclusion, right? So what this means is very important. In other words, it's like in law, everyone is assumed not guilty until proven guilty. You must have heard of that, and I think you wish that to be true, right? So everyone, why is that? Have you asked yourself, why is that? Why is it not that everyone is guilty until proven otherwise? Well, there are cases like that. Or certain crimes, certain kind of situation in law is the other way around. The accused has to prove that he or she is innocent, because otherwise, if you cannot provide enough evidence, then you are guilty automatically, even if there is not enough sufficient, not enough evidence to prove that you are guilty by default. That's, in the eyes of law. But otherwise, especially for very serious crimes, right? The penalty can be very severe, and if it is wrongly meted out, then that's very unjustifiable. So everyone is assumed by default not guilty, and that is the same posture we are taking here, right? For different reasons, because here we are assuming that the null hypothesis H naught is true. And what do you mean by is true? True, okay, I acknowledge it's true. So what, right? It's true means that, remember that the equal sign goes to H naught, right? The equal sign is always shifted to H naught. So the H naught always has an equal sign, which means that in our calculations, whenever we need to calculate mu, for example, converting to z value. So we have x minus mu in the numerator divided by sigma over square root n. So the mu in the numerator, what value do we put? In this case, for example, mu is anything lesser than or equal to 170. Should we put 150? Can I put 0? Can I put 1? Because it's still true, right? 1 is 1. If mu is 1, it is still true that H naught is less than 170, right? Yeah. So can I put 1? Answer is no. Put if you assert that H naught is true, then we take our calculation mu. Whenever mu appears in our calculation, we take that value as the hypothesized mean. So this guy here is called the hypothesized mean. And it has a nice symbol, mu0. This mu0 is knowable because we set it, right? The assertion sets this without proof. Just give a number, quantified number, right? So we will take mu equals to 170 whenever we need to calculate z value or any other situation where mu arises. Then we take it as if it is 170 first. Of course, that's asserted. Mu is not necessarily 170, but we're going to treat it as 170. That's why we say we will assume H naught to be true first, until otherwise invalidated by data. So data is so extreme that it cannot reconcile with this assumption. So we'll calculate, everything based on mu equals to 170, or based on mu equals to 100, or based on mu equals to 4.3. We'll treat it as true first. You see that in this case, the claim was 4.3. And so in our calculation, we also treat it as 4.3. Yeah. And then we proceed to sample and we calculate and we perform comparisons. If it doesn't force us to reject H0, then we don't reject H0. That H0 is true. And that's why the claim is true. Right. So we're going to assume H0 is true, right, until the data shows otherwise. Until the data is so extreme, by assuming H0 is true, data wouldn't hold. Okay, then we will reject H0. Okay, so that's the posture we take. Always remember this. Okay, so by default, innocent until proven otherwise. But or rather you remembering this, because we're talking about very specific part of the hypothesis, H0, and H0 is assumed to be true. And what does it mean by assuming to be true? We take the value of mu as if it is the mu zero, the number on the right side. So it's always good to express the number on the right side, especially when we talk about next in the 2 population or even 3 population, means test, then we need to remember to put the number on the right side. Okay, so that's the claim and hypothesis. Next, we want to talk about how to decide whether we should use Z or T. And for that matter, we have discussed that actually last time in confidence interval, right? So we're going to just quickly walk through again without trying to spend too much time justifying or discussing over the details. But first we need to ask, is X normal, right? Is the parent normal? Is the parent distribution normal? Do we know that it is normal? If yes, means that we do have normality, right? That's good. So what do? Well, then use that. For any sample size, regardless of n. Because parent is normal, then everything is nicely behaving. In that sense, we can just safely proceed, right? To use that. If I forgot to ask another question, is sigma known? Yeah. Okay, and if it is known, now that we use that. Okay, so let's back up a little bit here. Right here. And if it is not known, then we will have to use T. And for that matter, I was saying last time, or with most data sets. Because when you have a data set, right, such as when the exam or test question asks you to click here to download a data file and analyze it, that's a data set, right? So they have measured for you and recorded in the file, but you are to analyze it so as to score the point. In this case, when you have a data set, the question wouldn't tell you much about the population distribution, whether it is normal or not. So in this case, we will use T by assuming parent is normal. Okay, so this assumption is necessary because T exists only when parent X is normally distributed. Also, if parent is not normally distributed, you cannot use T. You cannot use T. So that brings us to the other part. If parent is not normally distributed, and for that we just use some zigzags, some weird bars and like that, right? So no, not normally distributed. Then in that case, we need to now check or ask another question. Is n large? Right? Yeah. If it is large, then what happens? We can use CLT. So by CLT, central limit theorem, we will use Z because central limit theorem specifically concludes that in this case, it gives you license to use Z for the X bar. It means the X bar. Look, X is the parent distribution. Is the measurement, the whole population set of measurements that we are trying to perform analysis on. So the distribution won't change. Whether if it is normal, it's normal. If it is not normal, we cannot force it to be normal. So what this means about using Z using T is that the X bar distribution will be normally distributed. The X bar. X bar is our own creation. So we can create anything to try to interpret our sampling distribution. But X itself cannot be changed. Yeah. Okay. So if n is not large, no, right, not large, then what we do is assume, all right, X is normal if possible. If possible means the question did not stop you from saying that let's assume X is normal. Yeah, because if the question is silent, right, is silent about this, is quiet about the distribution of X, for example, ask you to download the data file. That's it. Analyze and give the variance of the measured data. Fine. So you just say, okay, assume that X is normal, and then calculate variance, and then perform a test on this. Okay, so then you use T, because you can then assume that parent is normal. But if parent is not normal and n is large, then you can use CLT and you can use that. But if n is small, like 10, and parent is not described, then you can go, I need to draw carefully, all the way back up here, all right, by first assuming that X is normal, so that we go back up here and we ask again, is sigma known? If yes, then use Z. If not, then use T, right? But if you have a data file, then basically you assume X is normal and question did not tell you sigma. Sigma is unknown, so you will end up using T, yeah? So that's still consistent. And let me make sure this is properly highlighted. Okay, if possible, right? So that's when the question is silence about your ability to assume that the parent is normal. But if question is specific that you cannot do that, for example, the sometimes question will say, parent is known to be not normal. Oh, okay. So then it is dead meat here, right? Okay, so so I don't think the question will force you into this situation. Okay, because in this case, you really need thorough analysis of the actual distribution of X bar, which is painstakingly constructed one by one, combination wise, or you have to write a code to assemble the the actual distribution and then perform the calculations accordingly or for X bar, right? So this part becomes tough. I don't think your test question will lead you to this part, right? So most of the time you are able to route it back. Okay, so that's for answering or dealing with the next step, which is should I use Z or T? So hopefully with this diagram, you will be able to sort it out in a very quick and efficient manner. Next, let's talk about test statistic. Yeah? So we go about getting data. Sometimes the data is a data file, then you just calculate X bar and S. Yeah. So you're going to basically be given the data file, and then you calculate X bar and S. Okay, or else you're given sigma, and between S and sigma, you will trust sigma more. Okay, so this takes priority. Usually the question will give you sigma and not give you S. So they will tell you X bar is 150, sigma is 20, right? Perform a hypothesis test. Or they give you a data file and you calculate X bar, you calculate S, and you don't have sigma right now, yeah? So you know what to do. But tricky questions, sometimes they give you both. Or you get a data file and the question says, in addition, we know that sigma is 20. Then what are you going to do? Because your sample will give you a sample standard deviation. Maybe it's 19.5 or maybe it's 22. And your sigma is 20. Which do you trust? Of course, sigma. Of course, sigma. Because if you agree with me that when I have two samples, therefore I have two sample standard deviations, S1 and S2, the one with higher sample size wins, right? It's more reliable, it's more reflective, and more truthful about the actual sigma. But now I know the actual sigma, then why should I trust a estimation, a point estimation, correct or not? Yeah. So if S and sigma are both given, you will always take sigma. That's perhaps a tricky question, but that's always the truth, right? Because the whole point of calculating S is to point estimate sigma. Then you're given the sample size, of course, right? And you are also given alpha, the significance level. Okay, in a while I will show you where this is. And that would be the input that we need. Yeah. Okay, so whether it is Z or T, we'll use these cooking ingredients to calculate the test statistic. So we'll combine these to either Z or T. X bar minus mu naught over sigma over square root n. Okay, so this mu naught is this mu naught. Okay, and if it is T, then we will calculate similar to Z values formula, right? But because we don't have sigma, we're going to use S to point estimate sigma. And T is a pseudo distribution. That means it's very artificially constructed to approximate normal, adjusting for the inaccuracy that occurs when we use S to point estimate sigma. So that's actually statisticians' high quality worry that you and I may not appreciate very much, but they told us, right, that when you do this S as a point estimate of sigma, you lose some knowledge about reality, isn't it? Yeah, because we actually didn't know sigma. We didn't know the full extent of the fluctuation. So based on a few samples, and how can you trust that in the denominator this exact value is correct right now? Furthermore, it's in the denominator. So if sigma is 0.1 or if sigma is 0.2, that's going to be a big deal of a difference. So T is constructed in such a way to compensate for that uncertainty. That's all. That's all, right? So for you and I, for you and me, we don't need to worry about all these stories when we solve more important problems. We have a court case here. We have an argument here. We have a dispute here, right? We need to solve that problem first. So we just go about doing what is instructed of us to carry out calculating the test statistic. Now, what is this test statistic for? This is for putting into a diagram, okay? So putting into a chart. So this chart is going to be like this. And this chart is going to be X bar, never, never X. So we talked about this during the confidence interval video, right? That our measurements, our analysis, our conclusion in this case for hypothesis testing is always based on X bar because it's the universe that we can touch, measure, you know, using sample size n. And then make an inference or conclusion about X itself, or more specifically about mu of X itself. Yeah. So in this case, our X bar, because we will assume mu X bar, all right, to be mu 0. First of all, mu X bar is always the population mean of X bar. But in analysis, we learned that this is actually the same population mean value as X itself. X itself, right? So this is always true, whether we do hypothesis testing or not, because we use the expected operator, we have done this analysis. This is always true. But during hypothesis testing, that's when we exercise this statement. We are saying, what number should this be? Well, this should be equal to mu 0. And we're going to put in 170 here. That's the reason why we're going to put 170 here, because mu 0 is 170. Okay, so that's the whole idea. Next, we're going to say that, okay, and I will just draw, first of all, based on knowing either sigma or S, right? Whether you use Z or T, the shape is going to be looking very much like a normal, because basically, number one, that's in your syllabus, that's the only syllabus you have. And number two is that T is constructed to mimic normal as possible. And in fact, T becomes Z when n becomes infinity. Think about it. If n is larger and larger and larger, we finally know every single measurement in the population. So basically, you know, we do have the ability to know sigma very well. So T should then become Z. Not that it disappears, but then T is morphing into Z as n goes to infinity. Yeah, but then T will differ from Z quite a bit, right? Quite a bit when n is small, because the uncertainty is bigger and bigger. The knowledge about the population is lesser and lesser, right? So that's, now here we will draw this, and please sketch a diagram like this. Okay, so for this, we call this the right tail. Okay, that's good to put a note here and say this is the right tail. Right, because the arrow head is pointing to the right. Right tail test, like this. And this is the left tail test. And this is the two-tail test. Not no tail, but two-tail test. Okay. So at this point, alpha, let's talk about alpha. We have drawn this, and alpha example, 5%. Alpha typically will be 5%, 10%, sorry, 10%, 5%, maybe 2%, 2.5%, 1%, 0.5% is also possible. But anything smaller, 0.1%, 0.05%, it will be more and more suspicious. Anything bigger than 10%, like 20%, 50%, 80%, will attract more and more doubts and suspicion. Like, what are you doing? Are you trying to make sure, right, that H0 will never be rejected? Because if H0 doesn't get rejected, you get promotion. So I think you are trying to be funny here. You're trying to be fishy here, right? So if alpha is very large or very small, beyond those ranges from say 1% to 10%, all right, that's the safe range. People will not doubt you. Your published result will be respected. Your conclusion will be taken as is and then debated further about something else, not about your conclusion. But if your alpha is going to be 0.001% or 20% or 50%, then your conclusion itself may be rejected because people don't even, agree with the way you perform the analysis. Okay, so never do that. So what does that mean here? Well, the alpha equals to 5% means that for a right tail, you will shade 5% of area here. 0.05. So that's the 5%. Why must it on the right side? Because it's a right tail test. So this arrow points to the right. It means that when the test statistic falls into the right side, then we will reject. So the idea here is that this part is the rejection region. Okay, and in parallel, whether it's Z or T, Z or T is going to zeroize the mu zero. That means whatever value is mu zero comes to Z and T axis, it's going to be zero. And the shape is going to be the same thing. And the 5% is going to be the same thing. So I'm not going to draw another shape here. Just think of it as another parallel line to the X bar axis. So the X bar axis contains values that are making sense in our universe, our real life, right? So if this is $170 per month, X bar will have the unit $170 per month. But the Z and T is a virtual world, is a zeroized mathematical unit, like number of deviations away from the mean. And so it's going to look like 1 or 2 or 3 or 4. So we're going to say the equivalent of this is going to be how much? 1.645, let's say. Okay, so if you do the Q norm of 0.95 in R, because 0.95 is this part, right? They add up to 1. You will get 1.645. If you do a norm dot inverse, norm dot INV of 0.95, 0, 1, you will also get 1.645. So that's the sort of inverse cumulative distribution function, inverse CDF for normal distribution, or the inverse Z lookup table. You will get 1.645 here. And this is what we typically call the critical value. In this case, we have only one critical value because it's one tail. It's a right tail is one tail, left tail is also one tail. Two tail, there'll be two critical values, as we'll draw in a while. Okay? So at this point, you notice that here I have drawn everything before the battle. What's the battle? The battle is what's the reality saying, right? What's happening in real life? We have drawn all these just based on our own saying, our claim, our hypothesis, our significance level that is arbitrary because you can choose 5%, 2.5%, 1%, right? You can choose. Although not many choices, you still can choose. And you still can do all these drawings and calculations without the data. So no data yet, right? So you see that I have done all these drawings and positioning of everything, the battlefield, without any data at all. And now comes the data. That data is going to be summarized by the test statistic formula, right? So whether it's Z or T, the data will feed into X bar, will feed into S, and then N. It will be then summarized or converted into Z or T, one number, one real number only, And that number is going to sit on the T or Z axis, right, on this axis. So example, suppose here Z equals to, and you can always interchange the Z with something else. So if Z equals to 1.6, 1.55, okay, so it will be somewhere here, and basically that's our 1.55. So extending to the Z, to the X bar axis, we can draw a pin here, almost like a Google pin on the map, which is like a map, right? Except our map is just one dimensional. It's like anywhere on the x-axis. So the data is going to drive this pin more to the left, more to the right, yeah? Because it's going to affect the X bar and the S. These two are the moving parts driven by data. And when they both move, they will affect the final position of Z or T. Z or T, yeah? So this pin being driven by the value of Z or T will be more to the left or more to the right. Either way, we don't care. I mean, it's all up to the data. Yeah. So when the pin lies here, it is not in the rejection region, because rejection region is the section on the X bar axis that validates the H1, that supports the H1, that agrees with the H1. H1 says mu is 170, like this is 170 and above, greater than 170. So extreme that you have to accept that it's greater than 170. So 170 is here in the middle. Yeah. Any movements here is because we allow for statistical noise. Some influences, the factors of which we don't know and we are not concerned at this point. Some random fluctuations occur. Maybe our hands, shiver a little bit when we do measurements. Maybe typo error. Maybe instruments error. Maybe the Earth's magnetic field. We don't know. So the pin is going to move, hover around. And if it should be so extreme to be so much to the right that it breaches the critical value more than 1.645, then we will have to reject the H naught. And, we don't say accept, we say conclude that mu is greater than 170. However, as you can also see, there is a lot of space here on the X bar axis, on the x-axis here, the X bar axis here. There's a lot of interval, a lot of room of interval compared with the short interval here. By right, both will extend to minus infinity and plus infinity. But in the relevant section here, like plus minus 3 sigma here, there's a lot more space, right, for the pin to fall on. But don't get distracted by this. We don't care. We also we are unable to predict. Only the actual data will drive the pin. So there's no such thing as a high chance that it will happen in the middle or whatnot. Because if your mu X bar, this number 170, which is arbitrarily asserted by the person claiming such, right? If you move it to 0, the pin will not be more likely to be 0 than otherwise, correct or not? Yeah, because the pin is driven by the actual monthly billed amounts by the subscribers to the mobile company. So if it is hovering around 150, then 150. If it's hovering around 200, then 200. It would not be affected by this arbitrary number that you somehow pluck from the thin air. An angry person will say, yeah, I think the average is 250. Why not? They will say anything. Whereas another contented customer will say, are you sure? Every month I only pay $30. Right? So the person will put down 30 instead. Right? So the pin itself is not going to be moved by people like that. It's going to be moved only by the actual money, right? The measurements, the numbers that go into the measurements. Only then will the pin be affected by the changes in the data. Yeah. Okay. So that is the kind of outlook. And finally, just still on this diagram, we have seen test statistic, and that's this thing, right? So this is the test statistic. Almost like drawing a the anatomy diagram, right? Except this is for the hypothesis testing body. Critical value, we have the critical value here. These are static, right? As determined by the alpha. So critical value determined by alpha. Test statistic determined by data. What about p-value? P-value is determined by test statistic, therefore determined by data. How does p-value go? P-value goes, first of all, starts from the test statistic. Okay. We can try to write that down. P-value, p-value. Okay, so p-value. So p-value, right? The area that, which means the probability, because area is probability, starting from test statistic, because it is affected directly by the test statistic, right? Starting from test statistic and towards the infinity nearest how do I put it? Towards the infinity nearest the infinity. I'm trying to think of a more generic statement for the two-tailed case. So in this case, it goes towards the infinity of the rejection region. Okay, I'm going to update this for the two-tail case. This is applicable for one-tail case. Okay, so because I wanted to give you a description first before I start to execute it. So we're still doing one tail, so that's fine. Okay, so the area starting from the test statistic. So starting from the test statistic, right, towards the infinity of the rejection region. So towards the infinity of the rejection region is very clear because there's only one rejection region for one tail situation, right? So the infinity has to be here, like this. Yeah, and of course already you can see that it's more than 5%. And if the test statistic were to be in the rejection region, then the shaded region for p-value will be less than 5%. That's right. Yeah, so you can see that test statistic and p-value, they go hand in hand. Yeah, but when the test statistic doesn't cross the rejection region, we don't reject H0. Same thing, when the test statistic incurs a p-value that is outside the rejection region, the p-value will be greater than alpha, for sure, because it is by definition starting from that statistic, right? So you can see that it is going to be telling us to not reject the null hypothesis. Okay, so this is true, and this is also true for this. Now for the two-tail, we'll have to modify, but right now I hope you can digest this properly first, right? As to how to shade the p-value. You are a beginning learner, and you should, I would strongly suggest, sketch such a diagram, plot the test statistic, and shade the p-value region first. It's not difficult. The concept is very simple. The calculation, if you just look at formula, might be very daunting at first. What is p-value, right? And how does it work? P-value is, first of all, defined by the test statistic. So it changes when the test statistic changes. Alpha is fixed by our own definition. We decide, right? So it doesn't change. No matter what is the data, it doesn't change once we have started the hypothesis testing. Okay, so now let's try to perform another drawing for our second case example. This time round, I'm going to do a lot faster, and I'm not going to label so much and so extensively, because otherwise it'll be really very messy. But it also is very good in that I get to really show you how more compactly how it will be drawn or sketched maybe during your exam. Okay, so here we're just going to put a 170 here and a 0. And usually we'll also put down the standard deviation. But for now, I'm just going to skip that. So next, I have the alpha. And what we're going to do is to shade that. Oh, sorry. No. Because I was just mimicking this diagram here, and that's wrong. Okay, so okay, good, excellent. Yeah, I'm going to just quickly overwrite on top, right? Okay, then the alpha is going to be, because this is a left tail, can you see this? Okay, there's a left tail, the arrowhead of this less than sign. That's my secret here to try to easily remember it. Points to the left side. So it's a left tail of alpha equals to 0.05. I'm going to change another way to write it. It's also equivalent. And we're going to have the test statistic. Okay, so the test statistic example can be it's no longer 170, it should be 100 because pardon me. All right, good. So now I'm going to draw the test statistic and I'm going to like put it inside. All right, so it's going to be looking a little bit messy, but the Google pin is going to fall right here, whip, and cutting it down. Okay, number one, the rejection region is going to be here and to the left, right? The rejection region. Number two, the critical value will be, because it is still 5%, the value is 1.645, but since it's to the left of the zeros, it's going to be negative 1.645. Okay, and for the test statistic to land here, this number will have to be more negative than negative 1.645. So let's assume that's the t here, example t. T is equal to negative 1.844, example. That's why T leads this Google pin, this test statistic pin, to fall into the rejection region. And where is our p-value? Our p-value is going to be here, very tiny. Okay, so it's so tiny that it's a solid purple. And let me just draw this very, very carefully because it's getting denser and denser, p-value. And of course, this p-value region is clearly less than our alpha, right? So it is consistent. We compare p-value with alpha. We never compare p-value with test statistic. You will laugh, right? Of course not, right? But of course, students do. During exam or whatnot, they will like, since that statistic is minus 1.4844 and it is greater or smaller than p-value, right? And some people do that. And you don't use p-value to compare with the critical value, minus 1.64. neither do you use test statistic to compare with alpha. Of course, you now see why it's so strange, because test statistic and critical value, they are values on the z-axis. P-value and alpha, they are areas on the top bell curve or T-curve here. So how to compare, right? They are like totally different creatures altogether. Yeah. So p-value here. Okay. So far so good, because why do we know this is the p-value? Starting from the test statistic here. So far so good, right? We want to shade towards the infinity of the rejection region. The infinity of the rejection region now is minus infinity. So we will shade towards the minus infinity part. And that's why we have a very tiny value. And so we get a p-value that is 0.0005, for example. Very, very small. And it will lead us to reject the null hypothesis. Okay. Now, just a quick one to show the final two-tail version, which will have a bit of a which will necessitate a bit of a change, right, of the way we describe the p-value here. How so? Well, you already have guessed that there are, first of all, two rejection regions. Okay, so the center is going to be mu naught, is going to be 4.3. That's fine. I think we all understand that. Right? There's also a z or t curve, depending on which one we choose. And this will be the zero equivalent of 4.3. Fine. And now critical value. So not critical value, the significance level, right? Now, significance level, alpha is 5%, but we have 2. So we are going to break it into 2 halves. Of equal size. Okay, so here, this half will be alpha, not alpha actually. This part will be 0.025 because of half alpha, right? And this part is also 0.025 because this is also half alpha. Okay, always half, because normal curve, Z or T, they are symmetrical. So we have no reason to have one side bigger than the other. So far, so good. So this is the battleground, the static ground. No data yet. Then comes the data. Okay, now what happens? Now, so I'm going to make it non-rejection. Okay, so first of all, our rejection region are still very important. Okay, so this is the rejection region, which consists of the union of two parts, right? The left rejection region and the right rejection region. That means so long as the test statistic pin fall into either segment, then we reject, because that's the reason why we call it the rejection region, right? So when the Google pin falls into either of these RRs, we will reject. And what is the value of the critical value, right? So the critical value will now be the plus minus Q norm of half alpha. Because alpha is 0.5, so half alpha is going to be 0.025. So we'll take the Q norm of 0.025, and I get negative 1.96. And of course, the other side, positive 1.96. That's a common value you will see as critical value, right? Because alpha tends to be 5%. So when we get this, the test statistic will show some number. If the test statistic is negative 2, then it falls into this region, we reject. If the test statistic is going to be positive 1.99, then again it falls into the right rejection region, and we will reject. The Google pin, that means the test statistic that we draw, will have only one value. So for example, we're just going to call this the T. Okay, so no, the Z. Okay, so the Z. So we call this the Z. So Z equals to 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. 0.005. this will have to be a negative number, negative 0.8. Okay, so, okay, negative 0.8. Now what? Now what? Okay, what to know the p-value, you see we have a difficulty here. Just now, whether the test statistic is inside or outside, or even here, very extremely, we know that we should shade a big area, right? Because the infinity direction is very clear. Rejection region, that plus infinity, we just keep shading. Yeah, and if the pin is very much on the left, then the p-value is a very large number, 0.95, 0.99 even, right? And same thing here, if the pin is not so much into the rejection region, but over here on the far right, then we know where to shade. It's not this tiny right tail, but rather the big fat left tail that will make p-value very large. So it's still clear, no ambiguity. Over here, what happens is, should we shade to the left or shade to the right? Because rejection region contains both the minus infinity and the plus infinity. So what should we do, right? In this case, we need to include the word nearer, nearer, and also need to times 2. So let me, yeah, so let me put a bracket here for one tail case, right? The one tail case is just start from the test statistic and shade towards the infinity of the rejection region. This is so clear, right? Yeah. The two tail case, we will have to modify a few words, so I rather just start off with another paragraph. For the two tail case, the p-value is the area starting from, same thing, test statistic, from test statistic and towards the nearest infinity, and then times 2. That's something to think about. So let me delineate this. Okay, times 2. This 2 is very important because if you didn't times 2, you only get a partial p-value, which will likely lead you to do the wrong conclusion. Like you have a small p-value, then you decide to reject when actually you haven't times 2, so you shouldn't have rejected, but you rejected, right? So over here, what does it mean? So in our two-tail case, we have, let's say, right now z is either to the left of 0 or to the right of 0. So this part is easy if you say nearest. What is nearest? Nearest is of course minus infinity if z is negative. But if z happens to be 0.01, then it's positive, right? The nearest infinity is plus infinity. Okay, so what we do is we will first perform the area, calculate the area, right? So this is the area. This is half of p-value towards the infinity. So this is half of p-value. This is not p-value. We're not done yet, that is to say, right? This is half of p-value. What we need to do then is to times 2 so as to recover the full p-value. Another way to think about that is to say that I'm not going to draw it because it will make my already very squeezed colorful diagram more squeezed, more complicated, more noisy. So another way to think about it is there is another pseudo test statistic. Doesn't exist. We only have one pin. but you can think of it as having another virtual pin that is equidistant from the 0 mark, right? And we need to sum this tail and that tail. So that will be symmetrical, and so it will have the same area. That's the whole point of multiplying by 2, this half area here. Okay, so that's the way to think about it. The reason is because p-value is constructed to be a facilitating number for us to easily compare with alpha. So you see that if we define, all right, because you see I actually have another definition, p-value. P-value is doing this. It is a different step from the first one, right? If we define p-value to be the same, just go towards the nearest infinity of the rejection region. So then you'll be correct, because this is rejection region, there's only one, the nearest is also this one. Even if the pin is far away, there's only one, right? So this is the nearest rejection region, the infinity is plus infinity, we know what to do. Same thing for the minus infinity. And in this case, if we defined the area, this area, one side, one loop as p-value itself, okay, which is not the case, but I'm just saying, what if we do that? Then we have a problem, because we cannot compare this so-called p-value with half alpha. We are supposed to be comparing this with half alpha, right? So if we report this as p-value, then we have to compare with alpha divided by 2, because this, as you see, that this p-value can be easily larger than half alpha, and you are already in the non-rejection region, right? But then if you're just slightly larger than half alpha, like 0.026, then you are in the non-rejection region. But 0.026, that's less than 0.05, right? So what? We're supposed to follow the p-value and reject H0, or follow the test statistic and not reject H0? You see, we have a problem there. We have out of sync results. So whether you go by test statistic conclusion to reject or not reject H0, or you go by p-value comparison with alpha, it should be consistent. That should not have two different outcomes. So one way will be that, we know it's two tails, so whenever we see this so-called half p-value, we will compare with a divided half alpha. That's very troublesome. Another way is to so the responsibility is for the reader to know whether it is two tail, then we process the information. What about the other way, the current way, the prevailing way, is to say that the p-value is always comparable to alpha. Let's declare that, let's define that, all right? So the scientists, statisticians have established that we want a very easy way to communicate with each other, okay? Let's make p-value this device, this mechanism. So whoever produces p-value, the experimenter, the lab scientist, the doctor, the mobile phone company, the student, whoever produces the p-value or the test statistic and wants to also print out the p-value, is responsible to adjust for the fact that it's a two-tail situation. So whenever you measure this, times 2, please, right? So your p-value is the result of measuring this area, then times 2, so that whoever reads that p-value can readily compare with 0.05, alpha itself. Immediately, the person knows whether to reject H0 or not. You see, that comparison and reading, it becomes very easy. I don't even have to do a mental divide by 2 or times 2. Yeah, so that's the whole idea, making communication a lot easier. Now, as a quick try, why don't you just Google search for statistical report for COVID-19 vaccination effectiveness, right? So if those results didn't have statistical p-values, then look some more. there will be surely some medical reports, some lab results that have a bracket p equals to, right? They won't say p-value sometimes, they just say p equals to 0.01. What does that mean? That tells us that, hey, look, what I'm saying is really significant. It's statistically significant that we rejected the H naught, whatever H naught is. If you are bothered, then you go and find out what is the H naught, right? So they will make a claim. Our drug, our new vaccine is effective. Of course, you can guess from the person writing that lab report or academic journal submission to be making the claim. And if the claim is written by the author, then usually the title will reflect that, right? So efficacy of the new drug or something like that. So if you reject, means that yes, it is effective, right? So how to quickly understand that? They will put a bracket p equals to 0.01, p equals to 1.2 times 10 to the power minus 6, something like that, to show that it's very tiny, very, very small. Then you say, but what was the alpha you used? Now, remember I was saying alpha typically is 5%. If you want to change, not many values for you to choose. 1%, 2%, 2.5, 10%. Any other values outside the ranges? In fact, if you choose 8.22%, people will also question, are you really scientifically trained, right? Because typically it's just 5%, right? So that there is no special preference for larger or smaller p-value, alpha value, sorry, right? So whatever value you choose, if the p-value is 0.0000, many zeros and then a 1, then even if you choose alpha to be 1%, which is 0.01, only 1 0, right? And you've got so many zeros to protect you, it will be significant. Not to mention alpha is 10%, right? So just by publishing p equals to 0.0005, the scientist or the lab assistant, the analyst, the academic publisher already communicated a lot that, hey, look, I'm not bluffing. My p-value is this. So please try to believe me, right? So that's the whole idea. Yeah. So go Google around for some of these scientific reports, journal publications involving statistics. By and large, you will find p equals to something without saying much, right? And that's a very compact, efficient way to tell you my results are significant statistically, right? So don't doubt me. My conclusion is valid. Okay. All right. There is also one last but also a standard part, which is to say, how do you conclude, right? So already I gave a few hints just now, and is to say that conclusion, right? So how do we make conclusion? The short rule is whenever p-value is less than alpha, reject H naught, right? Another way is whenever test statistic is greater than the absolute value of critical values, absolute because just a compact way to say that when you have left tail and two tail involving negative, like this case, minus 1.645, minus 1.96, then your test statistic will be also negative, right? So it will have to be magnitude-wise larger than the critical value, right? So that is just a short mathematical way to say that test statistic exceeds, quote and unquote, because in the negative sense, exceeds means more negative, right? But then when you say exceeds, usually means greater than. But greater than means you are going towards the right, yeah? So long story short is, if you take the absolute value of both, the magnitudes comparison, so the magnitude is greater than magnitude, then you reject. Okay. And yeah, this part is also a little bit not completely, because it over covers the right side. Because what happens if my test statistic is 1.645? Yeah, so this is for the two-tail case. Reject H naught, right? And for one tail, then you need to check, is it left tail or right tail, right? So if it's left tail, then test statistic has to be lesser than the critical value. For right tail, test statistic has to be greater than the critical value. So rather hairy. Easiest is just to use the p-value. Okay, so the basic rule is that. And how do we write it? The way we write it is to say this. Since, right, it's a template. Huh? Since our p-value is equal to, example, 0.032 is less than alpha, which is equal to 0.05, okay, we reject H naught. And when you reject H naught, you don't look at H naught. H naught says this, you don't look at, because you have rejected it. It's not true in our findings, right? So we look at H1, we look at the other one, and say what it says, because it's a statement about the population mean, and say what it says in English. No Greek letter. Don't use mu. Don't use greater than. I mean, don't use a sign. Just use words. So we reject H naught. So if we use back this 170 case, we reject H naught and conclude that. Conclude what? Conclude that always conclude about the population mean, right? So the population mean monthly bill, whatever, put in the mu definition, right? So monthly bill is greater than $170 per month, comma, and you add this part at 5% significance level. So that means you repeat the alpha. Very important. Even though it's stated, even though it's given, you need to qualify your statement that you reject H naught because alpha is 5%. Yeah? Suppose alpha is 1%. Then what happens? The same p-value, right? Because the same data will end up being bigger than alpha. Then at that point in time, you do not reject. Correct or not? Yeah? So because the reject or not reject ends up becoming dependent on your choice. That's why you shouldn't know your p-value first. You have to first decide, oh, okay, let me set alpha to be 0.05. Let's say you don't like this result. You want it to be do not reject. You are a lawyer siding the mobile company. So you say, this is no good for us. Why don't we set our alpha to be 0.01? Then what happens? You didn't cheat. So, I mean, you did not do anything wrong because the data hasn't been modified. The data is correct. But we choose a more stringent alpha. Therefore, we tend not to reject H naught. So in this case, since p-value is 0.032, which is greater than 0.01, we do not reject H naught and conclude that the monthly bill is not so high, right? It's less than or equal to $170 at 1% significance level. That's why you have to qualify the reject, not reject conclusion. Yeah. And this is our conclusion. Right or not? Yeah. So all these are values to be substituted for each question. And the rest, basically, they are fixed template. So not much to not much creativity to think of, which is good because it means that you just fill in the blank. That's all. And that's nice, right? So why should hypothesis test be so difficult to do? It's very easy to do. Very easy to do. Okay, so at this point, let's just take a quick look at the whole picture again, right? That we want to do hypothesis testing because typically there will be a situation. The situation arises, can be a dispute, argument, right? Arrogance, proclamation, or for scientists, sometimes a suggestion, an idea. For doctors, medical practitioners, maybe there's a need to do certification, right? So we want to perform hypothesis testing. Is the patient having cancer or not, right? Maybe it is in the court of law. Is this accused, guilty or not guilty? Yeah. So we will first write down a claim. A claim is a statement about mu, and you want to define mu clearly because oftentimes the dispute, the arguments are very qualitative in nature, right? He is not so good. What do you mean by not so good? So quantify it. He is very talented. He is guilty. What do you mean by guilty? Measure guilty. No matter how difficult, you quantify it so that there's a claim about the mu of a number. Then we form the hypothesis, and the rule is all claims go to H1 unless the claim is about equality statement. So in this case, then the claim goes to H0. Then when we write down the hypothesis, and you are basically looking at all possibilities already. Of course, changing the numbers as per the question requires, but these are the three possibilities. Whenever we perform hypothesis testing, we will assume that H0 is true. What do you mean by that? Just saying that it's true. How does that help me? Because when we calculate test statistic, we need to perform X bar from the data minus mu. So what do you mean by assuming H0 is true is to say that mu, the actual population mean, let's assert it to be this number. Precisely this number, this 170 number, this 100 number, this 4.3 number, right? Of course, we don't have a proof because it is the very thing we are doing, right? But let's assume it's the case first until proven otherwise. That's the whole idea. So we assume H0 is true by taking the mu naught, right, as our mu throughout the calculations. And then we perform the calculations. And at this point, we need to decide, should we use X, Z, or T? And so we follow this map and decide to use Z or T. Then you do the test statistic calculation by extracting numbers from the question or the data set. X bar, S, sigma, N, and alpha. So all these numbers, actually not many, just, four, typically four numbers, and you plug it into the formula, which is pretty much fixed. Sketch a diagram. I strongly suggest, right, you sketch a diagram. Doesn't have to be accurate, doesn't have to be very nice like mine, very colorful. It can be just quickly sketched so as to know where is the tail. Very important because this could affect your sense of rejection region, whether to times 2 or not, that kind of thing. And where is how big or how small is your alpha? Where's your test statistic pin, right? Where's the zero line? Yeah, so all these are more about relative correctness rather than being exactly proportionately right. Okay, so after that is done, it's a good idea to roughly have a feel of where the p-value is. Now, when I say roughly have a feel, I'm talking about the left side of the loop or right side of the loop constitutes the p-value, and whether you should times 2 or not, whether it's half p-value that you are getting or not, right? So it's only clear visually when you sketch it out. Imagine I talk about all these by saying, like that, it's on the left and on the right, and you have to imagine throughout. It's so difficult, right? Yeah, and that's the way you will confuse yourself in the compressed time of taking a test or quiz. right? So your mind wouldn't be able to think straight. So have a sketch, and it's far easier to detect your any bug that you might have in the interpretation of p-value. Okay, and don't even um, get the idea that if I use R, if I use Python, if I use Excel, then it will be absolutely correct, right? Yes and no. All right, some of these functions, they have, are you doing two tail or one tail? I'll adjust for you, right? Whatever it is. But you will have to read the manual because it may not be the way you think, right? Certain functions might have its own behavior. And if you have the time to read the manual, I think it will be far shorter than the time you take to read the manual to just quickly sketch a diagram like this, right now. And you are much more confident, feeling much more secured and concrete, right, than to read a manual during test time of the kind of words that also might sound a bit foreign to you, right? Oh, set this two-tailed equals to true, meaning will return to you the two-tailed p-value. You know, things like that. It will be a bit of a guess and check on the try as we go, right? Even with R and Python. And so I will really say that it's a much safer idea, right, for you to do a sketch. Okay. And that's about it. And once you're done with this, you know that the test statistic is inside or outside the rejection region, or the p-value is smaller or bigger than alpha, then you can conclude over here. Right? So since p-value, or if you're doing test statistic, since test statistic equals to, in this case, 1.55, right, 1.55, and it is smaller than critical value of 1.645 over here, right? We do not reject and conclude that the population mean monthly bill is less than or equal to $170 per month at 5% significance level. So if it is do not reject, you just read what H naught says. If it is reject, you just read what H1 says in English, no Greek. Okay, and always remember we say reject or do not reject H naught. We only talk about H naught. We never talk about H1 in the conclusion. We only reject or do not reject. We do not say accept. Simple reason is just that we are not scientists here, right? We're doing statistics here. So this particular sample, this particular set of n samples resulted in a test statistic that led to this pin being in the non-rejection region. Imagine if you redo the sampling, the pin can float around here, right, due to noise, and may accidentally end up being in the rejection region, right? So we don't say we accept as a matter of absolute fact. See, the fact is we don't say that as a fact. So we don't really accept it as truth. We are just saying that we have to reject it this time, or we do not reject that, but doesn't mean we fully believe it, right? Because another sample might just end up rejecting or not rejecting again. So please stick with reject, do not reject, and stick with only using H naught and never H1 in your statistical conclusion. Okay, so with that, I think I'll end my video here. Thank you very much, and I'll see you in the next slide where we'll elaborate more about hypothesis testing and the conclusions and the potential errors we can make in our conclusions. See you then.